Hello and welcome to another fun-filled day of Math 102. This is your next video and today's topic is Pascal's triangle. So we're kind of getting into, between the last Zoom session and what we do in the next few classes, we're getting into a lot of different ideas about how patterns can show up and help us solve math problems. So another one of those patterns that shows up quite a bit is something called Pascal's triangle. So to start off with, I'm going to share what I'm looking at here. If you go to, this is page 39 in your packet. We went a little bit out of order there. But this introduction is an introduction to Pascal's triangle. And there's no title on this page really, but that's what I keep saying right here, Pascal's triangle. What I'd like you to do is take a minute, pause the video real quick, just read through this so you have a bit of background. So go ahead and do that and press play when you're ready to go on. Okay, so assuming you've read through that paragraph, what is Pascal's triangle? Well, if you go on to the next page in your packet, so I'm going on to page 40 now. You'll see this says Fibonacci numbers in Pascal's triangle. We'll deal with what Fibonacci numbers are in a couple of classes, but for now, I just want to show you how this triangle is made. So Pascal's triangle always starts with 1 on top, and the next row also has 1s. And basically, to get any other digit, the sides are all going to be 1s always, and anything in the middle comes from the sum of the two numbers above it. Okay, so like if I'm looking for this spot, 1 plus 1 is 2. So that's that row. The next row, I have 1 plus 2, that's 3. Here I have 2 plus 1, so that's 3. Think about what the next row would be. What's going to be here? 1 plus 3 is 4. The middle number will be 3 plus 3, 6. Then 3 plus 4 again is 4. 3 plus 1 again, sorry, is 4. So you'll notice because both of the sides of the triangle always end in 1s, there's always going to be this symmetric pattern to it. It's going to increase to the middle number and then start decreasing back to 1. So go ahead, fill in these last two rows. What are they going to be? Well, this would be 5, 10, 10, 5. And again, I'm always adding the two numbers directly above it to get the one in the middle. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15 again. 5 plus 1 is 6 again. And if you could just pause the video again, take a couple minutes, fill in all of these missing pieces that are left, just to make sure you've got it. Okay, you ready to see the answers? Well, this would be 15 plus 20, it's 35. 70 plus 56 is 126. And you can also kind of do symmetry. If you count 1, 2, 3 in here, I got 45. So 1, 2, this should be 45 as well. And you can see that it is 36 plus 9. Similarly, what should that be? Well, 1, 2, 3, 4 in. 1, 2, 3, 4 is going to be 120. Again, if you look at 36 plus 84, that is 120. This spot here is going to be 126 plus 84. That's going to be 210. No big surprise because of what's there. 10 plus 45, that's going to be 55, which matches over here. And 210 plus 252 is going to be 462, which matches what's on the other side there. Okay, so that's how to make the triangle. Ease peas? I hope so. All right, moving right along. Okay, so now we're going to get into some activities that might take a little bit more work. So I'm on page 41. And you can see that this is called counting polygons. It says in the diagram below, there are 5 points on a circle, and those are joined by line segments. The questions say, how many line segments are there? How many triangles are there? We're only going to count the ones with vertices on the circle. How many quadrilaterals are there? Quadrilaterals means it has 4 sides, like a square or a rectangle. And how many pentagons are there? How many sides does a pentagon have? 5. So to make it a little bit easier on you, what I would suggest doing is label these vertices. Let's call this A, B, C, D, and E. So to count the line segments, you could probably just count them up by drawing. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And just by tracing over them, I can count all those. Now, stuff like this arc from B to C doesn't count because an arc isn't a line. A line has to be a straight line between 2 points. So there are 10 line segments. Now, another way to do that is to think about every line segment has a letter attached to another letter. So if I've got A, B, C, and D, and I wanted a line segment, there needs to be 2 vertices, A and B. So I could do A and B, A and C, A and D, A and E, and then I can start with the B's. So I don't need to say B and A because this line segment is the same as this line segment, right? So B with every letter that comes after it. So B and C, B and D, B and E. And do the same with C, C and D, C and E. Again, you only need to use the letters that come after it in the alphabet because any that came before we've already got. There's C and B. And then the last one would be D and E. And if you count those up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Now the reason I showed you this way was if you're methodical with how you write them, it'll be a little bit easier to keep track of them. Because once I get to part B, how many triangles are there? And we're only going to count those with vertices on the circle. So what I mean by that is like this triangle here that I'm kind of tracing out wouldn't count because these 2 vertices aren't on the edge of the circle. So it's got to have a letter on the edge of the circle as one of the vertices. You can see this is going to get tricky to count out if I just try to draw them all out with my marker. So all we need to do is think about how many different combinations of 3 letters can I get together, basically. So let's see if we can list them. I'm going to try to be methodical about this too. Let's start with A, B, C. And let's do all the ones we can do with A and B. So we have A, B, C, that's one triangle. A, B, D, that's another triangle. And A, B, E is another triangle. So I did everything that started with A, B. So what would it make sense to do next? Let's do AC. I don't need ACB for the same reason. That's the same as triangle ABC. But if I do ACD and ACE, I'll get those 2. Now we've done all the ABs, we've done all the ACs. Go for the ADs. ADE is the only one you can do, I think. So now I've taken care of everything that starts with A. Now let's start with B. So I don't have to consider A because I should have everything that has an A involved. So start with B, C, D. And then let's do B, C, E. I think that's probably all my BCs I can do, but go to BD, BDE. Now there should only be one left because when I move on to the C's, there's only one option, C, D, and E. There's no other letters that come after those. So count it up, how many triangles have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 triangles as well. Okay, moving on to quadrilaterals. Again, how many sides does a quadrilateral have? 4. So we're going to see how many lists of 4 I can do. Again, be methodical. Start with A. So I'm going to do A, B, C, D. What else could I do? I'd stick with A, B, C and go with the E now. And I think that's all I can do with A, B, C, but I can do A, skip over B, and do C, D, E. So A, C, D, E. Is that all the A's you think? A, B, C, D, A, B, C, E. Oh, there's another A, B I can do. You see it? I could do A, B, D, E. I could skip over C. And I think that's all I can do with the A's. This gets a little trickier to count. So what's the only other one if I didn't have A involved? B, C, D, E. Another way to think about this is all of the 4 combinations are going to have 1 letter missing. So how many ways are there to have 1 letter missing? Well, if there's 5 options, there should be 5 ways to have 1 letter missing. This doesn't have E, this doesn't have D, this doesn't have B, this doesn't have C, this doesn't have A. That helps. That's another way to watch it. So there's 5 quadrilaterals. Now, the last thing says how many pentagons are there? And that should be soupies. How many pentagons? Pentagons have to have 5 vertices. And how many vertices do I have? 5. So the only possibility for pentagons is to use all of them. A, B, C, D, E. So there's 1. Okay. So this can get a little tedious, but I want you to take a few minutes, pause the video. I want you to try number 2. And number 2 is actually a little bit easier than this one that I did with you because there's only 4 vertices, 4 points on a circle. So it says, I'll start you off. There are 4 points on the circle, connect every point to every other point. Let's label them. A, B, C, D. And if I connect every point to every other one, it's going to look something like this. Okay, so now you go through and answer the 3 questions down there. How many line segments, how many triangles, quadrilaterals, I guess there's 4. D, how many pentagons. Okay, so do number 2. And then number 3 might be a little bit trickier because there's 6 points on the circle. So we're gonna have to label this one A, B, C, D, E, and F. And again, we're going to connect every point that we can. Connect all the A's, all the B's, all the C's, all the D's, all the E's, and then by the time you get to F, you have them all. And see if you can answer those 4 questions. Okay? So probably take about 20 minutes, I would say. Do number 2 and 3, and then we'll come back together and see how you did. So pause the video and give it a shot. Good luck. Okay, let me go through and you can see if you missed any and you can see how you did. How many line segments? So for number 2, we can have A with B, A with C, A with D, or we could have B with C, or B with D, or we could have C with D. You should have had 1, 2, 3, 4, 5, 6. And again, the line segments, you probably could have also just counted. 1, 2, 3, 4, 5, 6. Okay, let's do how many triangles. Do all your ABs first. AB with C, AB with D, and move on to ACs. ACD, Okay, then we can do anything with B's. That's just B, C, D. And it looks like I'm done already. It's only 4 triangles. Quadrilaterals should have only gotten 1, A, B, C, D. You need all 4, so there's only 1. And notice for B, how many triangles are there? Again, it's basically saying you have 4 vertices. How many ways can you leave out one of the points? This has no D, this has no C, this has no B, this has no A. There's 4 ways to leave it out. How about pentagons? Well, if you need 5 points for a pentagon and there's only 4, then no pentagons. Okay? All right, don't put that page too far away because I'm not quite done with it. That's what you should have gotten for number 2. Then number 3, like I said, is going to be a little bit more annoying just because of how many points there are. So if I was counting all the line segments, we've got A, B, A, C, A, D, A, E, A, F, do all your B's, B, C, B, D, B, E, B, F, all your C's, C, D, C, E, C, F, all your D's, D, E, D, F, and finally all your E's, E, F. Do you remember what problem we kind of did this earlier on? You might have started noticing the pattern. This is 5 plus 4 plus 3 plus 2 plus 1. It's like the handshake problem. So 5 plus 4 is 9, and 3 is 12, and 2 is 14. We should have 15 line segments. Triangles get a little tricky to count. Take all of your ABs. We have ABC, ABD, ABE, ABF, and then take all of your ACs. ACD, ACE, ACF, then take all of your ADs. ADE, ADF, and finally all of your AEs. AEF. And that's just all the ones that start with A. Now we got to start with B. BCD, BCE, BCF. Now do your BDs. BDE, BDF. All your BEs. BEF. Got our A's, got our B's. Let's move on to C's. CDE, CDF. I think that's it. We can do CEF. Okay, I think that's all those. And then finally the D, DEF. Let's count them up, see if we got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 it is. And that's the right answer. There's 20 triangles. If you missed one, see if you can come up with the one you missed in the list. All right, moving on to quadrilaterals. All right, these ones are tricky for me too. We've got A, B, C, D, A, B, C, E, A, B, C, F. That's all my ABCs. Now let's do ACs. ACD, ACD, E, and ACD, F. How about ACEs? ACEF. Okay. How about ADEs? ADEF. I get them all? ACDE. Okay, we'll come back. I think I got them all. Let's do, is that everything that starts with an A then? I think that might be. We'll come back if I missed some. Now let's start with the B's. B, C, D, E. B, C, D, F. B, C, E, F. And I think that's it. Okay. I feel like I might be missing some. We'll see what happens. How about my C's? Well, there's only one C I can really do. C, D, E, F. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm definitely missing some. There should be some more. Let's see what I missed. Oh, how about BD? B, D, E, F. There's another one. About my A's, I've got those. Oh, what if I skipped over C? What if I did A, B, D, E, and A, B, D, F? So I got a couple more A, D, B's, and I can skip over D as well and do A, B, E, F. I think I might have them all now. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are supposed to be 15 of them. So my purpose with this last one here, how many pentagons are there, is to show you that this brute force way of listing them all is starting to get obnoxious, right? It wasn't so bad with the earlier ones. There's got to be a better way, and there is. We'll get there. How many pentagons are there? So I need 5. 5 points. So A, B, C, D, E's the easiest one. Let's do A, B, C, D, F also. And again, if you use my trick, if you need 5 of the 6 points, I'm basically saying how many ways are there to leave out 1 point? Well, there's 6 points to leave out. My answer should be 6. So here, A, B, C, D, E, I left off F. A, B, C, D, F, I left off E. Let's leave off D now. A, B, C, E, F. Let's leave out C. A, B, D, E, F. Let's leave out B. A, C, D, E, F. And let's leave out A. B, C, D, E, F. That should be all of them. Okay, so I mentioned that there is actually a better way to do this. So what is it? Well, if you move on to page 43, I'll show you. Let's complete the following table. Now, on this top thing here, I've only got 1 point. So we've got 1 point, and all of these are going to be zeros. I'm just going to leave those blank because I can't have any line segments if I only got 1 point. The second one here, I have 2 points. I have 1 line segment between those 2 points, and I can't have any triangles because I don't have enough points. The third one, I have 3 points. I have 1, 2, 3 line segments. And I have 1 triangle. Now this fourth one we already did. If you flip back to page 41 real quick, that's this one. We had 4 points. We said there were 6 line segments. We said there were 4 triangles. We said there was 1 quadrilateral, and there couldn't be any pentagon. Are you starting to notice anything? If you're not, let's do a couple more. This one, that was like number 1, the one I did with you. There were 5 points. There were 10 line segments. For triangles, we also had 10. We had 5 quadrilaterals and 1 pentagon. There'd be nothing after. And the last one that we actually did on page 42 had 6 points. It had 15 line segments, 20 triangles. So 15 line segments, 20 triangles. Another 15 quadrilaterals, 6 pentagons. 15 quadrilaterals, 6 pentagons. And I didn't ask for how many hexagons, that's 6 points. But if I have 6 points, how many hexagons would there be? Only one that would take all 6. So what we're actually seeing here is something that you saw earlier today, and it is called Pascal's triangle. Now notice it's kind of just part of Pascal's triangle. I chopped off the 1 on the left-hand side of all of these, so all these 1s are missing. But other than that, you kind of see them side by side. There's 1, 2, 1, 3, 3, 1, 4, 6, 4, 1, 5, 10, 10, 5, 1. So if I kept going, it would just be doing Pascal's triangle. This would be 7, 21, 35, 35, 21, 7, and 1. And think about how obnoxious that would have been to count all those points. We don't have to. When there's 8 points, we know it's going to go, okay, I'm just kind of reading off this line, 8, 28, 56, 70. Imagine counting 70 quadrilaterals. Blech. 56, 28, 8, and 1. When there's 9 points, it's going to be 9, 36, 84, 126, 126, 84, 36, 9, and 1. And then finally, when there's 10 points, imagine counting everything up in there by brute force. It would be 11 line segments, 55 triangles, 165 quadrilaterals, 330 pentagons, 462 hexagons, 330 heptagons, which is 7-sided figures, 165 octagons, 55 nonagons, well, that's annoying. I copied the wrong row. Sorry. Don't hate me. You look at that row. There would have been 45, 120, 210, 252, 210, 120, 45, 10, and 1. Okay, sorry for that last mistake there. Ruined my climax here. Anyways, there's a reason why Pascal's triangle is showing up here. And once we do the next activity, I think you'll see why. All right, moving right along. Number patterns. This is page 44 now. Find the sum of each row of Pascal's triangle. Let's just do this one together. So the top row is just 1. 1 plus 1, that's 2. 1 plus 2 is 3, plus 1 is 4. 1 plus 3 is 4. This is going to end up being 8. This one's going to be 5, plus 10 is 15, plus 1 is 16. Now there's a pattern happening here too. 1, 2, 4, 8, 16. Any guess what this next row is going to be? Think about how one number relates to the one before it. We're multiplying by 2 every time. So this next one's going to be 32. And let's see it. Let's check it. If you think you have a pattern, you should always check. 1 plus 5 is 6. Plus 10 is 16. Another 10 is 26. Plus 5 is 31. 32. Yep. And it turns out that this works. If you add all these up, you'll get 64. Add all these up, you'll get 128, 256, 512, 1024, and 2048. So the pattern is the sum of each row is double the sum of the previous row. And if you think about it, it's just kind of a crazy coincidence. You could probably prove the math somehow. But remember, we just formed this triangle by adding two numbers above to get the one that would fall below in the next row. And it just happens that when you do that, the sum of all the rows are always double the one before it. Now, another way to write this, we're going to get into sequences in a couple days. This is essentially called a recursive sequence. Don't worry too much about that right now, but it relies on you knowing the previous row. Like if I wanted to know the sum of this last row down here, I wouldn't have been able to tell you that unless I got all the way down here. So if I want the sum of the 20th row, well, I can figure it out. I'm going to have to double 19 rows before it to get there. That's called recursive. Something nicer would be an explicit sequence. And these are all powers of 2. This is 2 to the first power. This is 2 to the second power. This is 2 to the third power. And even this one works. This would have to be 2 to what power? 2 to the 0. Anything raised to the 0 power is always 1. 2 to the fourth, etc. So if you notice it, if you want to find the sum of a particular row, what's this one going to be? Well, this was 2 to the fourth, and there's a 4 here. This is 2 to the third, and there's a 3 here. So whatever that second number in the row is going to be your exponent. Here, there is no second number in the row, so it's 0. So 2048 should be 2 to the what? It's a 1 there. The 11th. So another way to think of it is it's 2 raised to the, now count it out. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is actually the 12th row. It's 2 to the row number minus 1. So if I wanted the 4th row, it's 2 to the 3rd. If I want the 5th row, it's 2 to the 4th. The power is always 1 less than the row number that I'm on. Row 1 is a power of 0. Good? So for example, if I want to use what I have already really quickly, if I asked what 2 to the 10th was, what would it be? Well, you look for the row with 10 in it. That should be 2 to the 10th, 1024. And 2 to the 11th we kind of already did. It's the row with the 11 in it, which is 2048. All right. Okay. All right, if you ever need a break through any of this at all, I know it's kind of long, but these videos are essentially a 2-hour class that you're not sitting in. Obviously pause the video, go later on, but we've got a couple more things to do today. Let's move on to page 45. How many ways? Now this one I liked because it kind of puts together what we did with that counting polygons worksheet and why it worked out to be Pascal's triangle. Number 1 says take 4 different colored blocks. How many ways could you pick 2 of these blocks? And assume that 1 red block and 1 blue block is one way, whether you pick the red first and the blue. So red-blue is the same as blue-red, like we've been doing with all these. So I'm going to try to use some colors here. Let's say we've got 4 blocks. We've got a red, we've got a green, we've got a purple, and I'm going to have a blue. You obviously don't have to use different colors on your notes unless you want to. I just wanted to try to show different colors. I know purple and blue are kind of hard to see there. But anyways, I want to know, with those 4 colored blocks, how many ways could you pick 2 blocks? So I could pick red with green, red with purple, red with blue, just like I was doing earlier. I could do green with purple, green with blue, or I could do purple with blue. 1, 2, 3, 4, 5, 6. how many different ways could you pick 3 blocks out of the 4? We can do that too. We can do red, green, purple. We can do red, green, blue. We can do red, purple, blue. Or we can do green, purple, blue. Basically, how many ways are there to leave out one block? So there's 4 blocks. I can leave out each of them once. So there's 4 ways. The symbol, so I got a parentheses with 4/2, means the number of ways to pick 2 objects out of 4. So it's probably a symbol most of you haven't seen before. Just think of it like the square root means, you know that means like the square root of 49, you know means 7. Just another symbol that means something in math. You might have seen it at some point in your math lives, maybe not, written as 4 choose 2. Either way means the same thing. Or you may never have seen it, and that's fine. So essentially, in problem 1, we found out that 4 choose 2 was 6. Out of 4 blocks, how many ways to pick 2 of them? There were 6 ways. And in problem 2, we found out what 4 choose 3 was. Out of 4 blocks, how many ways could I pick 3 of them? What would 5 choose 2 be? Well, I would need 5 blocks. So let's say I had that red, green, purple, blue, and let's add an orange on there. If I want to know what 5 choose 2 was, I'd have to figure out how many ways are there to pick 2 blocks here. So we can do brute force. All the reds, then all the greens. If you remember the shortcut from handshakes, you could do that way also. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5 choose 2 is 10. Now it says finish filling in the answers below. Mathematicians say 0 choose 0 or 1 choose 0, 2 choose 0 are all equal to 1. There's really only one way to pick nothing out of a pile. You have the pile, how many ways can I pick nothing out of it? I can pick nothing, so it's one way. But it also helps make this pattern look a little nicer. So I filled all those in as 1s. 1 choose 1. If I've got 1 block, how many ways are there to choose 1 block? I can take the 1. That's it. If I have 2 blocks, how many ways are there to choose one of them? I could take the green or I could take the red. There's 2. But if I have 2 blocks, how many ways are there to pick both of them? I'd have to take both, so just 1. If I have 3 blocks, how many ways are there to pick 1? I can pick block A, B, and C. If I have 3 blocks, let's move to this one. If I have 3 blocks, how many ways are there to pick all 3? Just 1 again. What do you think 3 choose 2 would be? Well, hopefully, based off of the way I drew this, you can see we've got Pascal's triangle again. So what should it be? If this is 2 and this is 1, this should be 3. And if I've got 3 blocks and I'm picking 2 of them, I can pick AB, AC, or BC. So there's 3. For this row, out of 4 blocks, there's 4 ways to pick 1 of them. We already set up top that 4 choose 2 was 6. And we have that 4 choose 3 was 4. And there's only 1 way to pick all 4 out of the 4. So these, again, it's called combinations. That's why I keep saying choose. You're finding how many combinations, ways to get them there are, is really just Pascal's triangle. And can you see why that would relate to what we did earlier? Look at this one. How many line segments are there? When I had 1, 2, 3, 4, 5, 6, this is back on page 42. When I had 6 vertices, if I did 6 choose 2, there'd be that many line segments. And there's actually a way to do this on your calculator. If you have a graphing calculator, if you don't, there's probably a way to do it too, but don't worry about it. I can do 6, then go to math, over to probability. That NCR is the combination stuff we're doing. If I do 6, choose 2, there's that 15 number again. If I wanted triangles, I'd be saying, okay, out of my 6 vertices, I want to pick 3 of them. And if you do 6, choose 3, there's your 20. So that's the shortcut way. And you can see why Pascal's triangle related to this question was because we were really all just finding combinations. Quadrilaterals would have been 6, choose 4. Pentagons would have been 6, choose 5. Out of my 6 vertices, how many of them do I want to pick? The last part of this, back on page 45 here, the last part of number 5, does this triangle look familiar? Of course it does. It's what we've been doing all day. Use the pattern to guess how many ways you could pick 3 objects out of 6. So I want from 6, choose 3. And we could write it out like this, or now I could use the triangle. I know the next row is going to be 1, 5, 10, 10, 5, 1. But this would be 5, choose 0, 5, choose 1, 5, choose 2. I need 6. So I need one more row. It'd be 1, 6, 15, 20, 15, 6, 1. I want 6, choose 3. This is 6, choose 0, 6, choose 1, 6, choose 2, 6, choose 3. Should be 20. And if you go back to that pentagon example we just did, or the hexagon, I guess, on page whatever it was, we've got that out of my 6 vertices when I was doing triangles, we had 20. It all connects. All right. Hopefully you're doing okay. As always, if you got questions, please write them down. Please email or set up a time to meet with me. I'm happy to do that. We got one more activity today. It's called Patterns in Pascal's Triangle. So right now I'm looking at page 46. I'm going to start you off on these and have you try a couple on your own. Number 1 says a hexagon is a figure with 6 sides. Draw a hexagon around a group of 7 numbers in Pascal's triangle. So here's a mini Pascal's triangle, and here's how I drew a hexagon. So I've got 2 numbers on top, go down 2 numbers, over 2 numbers, 2 numbers on the bottom, go up 2 numbers, over 2 numbers. Okay, so I've got a hexagon. Look at any side, there's kind of 2 numbers adjoining any side. Add the numbers and divide by 2. So I'm going to take all the numbers inside. So 3 plus 3 plus 4 plus 6 plus 4 plus 10 plus 10. It says to add up all those numbers and divide by 2 and see what we get. I can do that. 3 plus 3 plus 4 plus 6 plus 4 plus 10 plus 10. Divided by 2, we get 20. Do 4 more hexagons on the large triangle. Have you found a pattern? So if you flip past page 47 for a second, and go to page 48, there's a giant Pascal's triangle. I did one of these for you, this one here. I drew a hexagon, added all the numbers inside, divided by 2, and I got 20. Pick another hexagon. Let's say I do right here. I'm going to take these 2 numbers, and these 2 numbers, these 2 numbers, these 2 numbers, these 2 numbers, these 2 numbers. The directions say to do 4 more of these. So here's 1 more. Add up all those numbers, divide by 2, see what you get. Then do it 3 other random places on here and do the same thing. See if you can figure out what's happening. Okay, so go ahead, pause it for a second. Try that. Again, the first thing I want you to do, go to your page, this is page 48 now. Draw one of those hexagons. You can use the one I just drew for you here. Add them all up, divide by 2, see what you get. And then do it 3 more times. So always doing hexagons, 2 on a side, 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 2 on a side. Draw your hexagons anywhere you want. Should be 4 total when you're done. And show me what your calculations are and see if you see what's going on. Okay, so pause it and try that. Did you figure out the pattern? Okay, let's see. So the ones that I just drew here, if I add up these numbers, this is 5 plus 10 plus 6 plus 15 plus 20 plus 21 plus 35. That's 112 divided by 2 is 56. So the answer to that hexagon was 56. And then I just picked another one down here. You might have different ones. That's totally fine. 792 plus 495 plus 1716, I think that is. That's 1287. It's a little hard to read. Plus 715 plus, what's that, 3003 and 2002. Divide that by 2 and I get 5005. You starting to see the pattern? Where is that number that you got on Pascal's triangle? Right below it. In every instance, that answer was right below it. And that's always going to happen, kind of just a crazy coincidence. Now let's say I picked these. Just picking a random hexagon. Before you do anything, what should the answer be when you add all these up and divide by 2? Well, the answer is always right below it. So it should be 680. Let's double check it. 14 plus 91 plus 15 plus 105 plus 453 plus 120 plus, what's that, 560 divided by 2. Oh, I must have gotten off a number. Give me 679. What did I do? Let's check. 15, 19, 14, 91, 15, 105, 453, 120. Double check all my numbers here. Is this really 453? Oh, that was 455. That's the problem. These numbers get a little small to read in there. 680. There we have it. So that's going to work anywhere on the triangle. If you go back to page 46 here, for my pattern, I would just say answer is the number directly below the hexagon. Every time. Number 2 is a little bit easier to do. It says, using the same hexagons from above, place circles and squares on them as shown. For each hexagon, find the product of the 3 numbers with circles and find the product of the 3 numbers with squares. What's product mean to do? It means multiply. And we're looking for a pattern. So you can see in the 2 hexagons they drew down here, if I do this one, I want the product of the 3 numbers with circles. So in this case, it's 5 times 20 times 21. This is 2100. And the 3 squares. So 10 times 35 times 6. What do you notice? They're the same. Is that going to happen over here? Let's try it. 5 times 1 times 21, taking the 3 circles. It's 105. And 1 times 7 times 15. Also 105. So the pattern is they're the same. Just another crazy coincidence that shows up in Pascal's triangle. If you alternate circles and squares, multiply the circles together, multiply the squares together, in that hexagon, you're always going to get the same answer. Crazy. Okay, last one. Page 47. On the second large Pascal's triangle, so if you flip over to page 49, you'll see that, draw parallelograms of varying size. Your parallelogram must start with the top of Pascal's triangle. So a parallelogram just means opposite sides are parallel. So this one is actually a square. For each parallelogram, sum the numbers inside and add 1. So that's what we're supposed to do. Sum the numbers inside, add them together, and then add another 1. So like for this one, I'm going to do 1 plus 1 plus 1 plus 1 plus 2 plus 1 plus 3 plus 3 plus 6. That's the sum inside, add 1. I get 20. Circle the result on the triangle. There it is. Try it again. Here's another possibility. So if I do 1 plus 1 plus 1 plus 1 plus 2 plus 1 plus 3 plus 4. It's 14, then add 1. We get 15. Circle it on the triangle. There's 15. Huh. Okay, so if you go over to page 49, you just have to make a parallelogram. It has to start at the top, so you can't start in here. So let's say I take, I don't know, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. I go 8 down this way. Let's go 4 down that way. I have to go 4 down this way as well, that means. Then this should be 8 up this way. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Based off of what you saw a second ago, so let me pull that sheet back out. When I add up all the numbers inside and add 1, look at where it showed up. What do you think the answer is going to be here? Circle what you think the answer would be if it matches the same pattern. Now let's try it. 1 plus 1 plus 1 plus 1 plus 2 plus 1 plus 1 plus 3 plus 3 plus 1 plus 1 plus 4 plus 6 plus 4 plus 1 plus 5 plus 10 plus 10 plus 1 plus 6 plus 15 plus 20 plus 1 plus 7 plus 21 plus 35 plus 8 plus 28 plus 56 plus 36 plus 84 plus 120. I get 494. When I add 1, 495. Right there. It always seems to be that bottom vertice, that bottom point of the parallelogram, just points to the answer. Points to the answer, points to the answer. That's kind of how I wrote it. The bottom vertice points to the answer. Isn't math crazy? I don't know why it works. It just does. So fun. All right. You're now experts on Pascal's triangle. Let's talk about your homework. You have 2 questions to do for homework. First is called Bernoulli's table. This is on page 50. It says this table was published in 1713 in the book Artis Conjectandi by Jacob Bernoulli. Do you see any interesting patterns? Can you figure out what the next row would be? So your goal is to write what this row is going to be here. It's obviously related to Pascal's triangle. See if you can figure out how. All right, and then the other one I want you to do is page 51. Page 51 is called Moving Checkers. It says the checkerboard shown below contains 1 checker. The checker can only move diagonally down the board on the white squares. And how many ways can the checker reach the square marked A? So for example, how many ways can I get to this spot? I can only get 1. There's 1 way to move. Just like that. Similarly, there's only one way to get to this spot. Technically, how many ways are there to get to this spot? Well, if I can only move diagonally down the board, there's no way I can ever get over there. So there's 0 ways to get here. There's 0 ways to get here. How many ways could I get here? 1. I can just go slide left, slide left. It's the only way I can get there. But how many ways can I get here? Well, I can go this way to here, or I can go this way to here. There's 2 ways to get there. So see if you can figure out how many ways there'd be to get to spot A. And again, Pascal's triangle does come into play. All right? All right, so that's the end of this lesson. You need to show me basically page 40 through 51. If you take pictures of page 40 through 51, that's everything we did today. So send me those. The last 2 questions are homework, so you don't have the answers to them yet, but I'll go over them in our next Zoom session. Send me those and you're officially done with this lesson. Good luck.